So we're not worrying about fermions. We're going to toss these things in, toss in later. Okay? Then, when we get all done with that, and this is what we're going to continue with today, is we're going to improve many atom model by tossing in a E potential. Right? But it will still be one electron. And we'll toss in that they're fermions. So make many, and we'll make this all later. Okay? So, everybody kind of get the idea? I haven't done this yet. We did this, but I did not say so explicitly what we're doing. Okay, so the way you always start off with the solids and the electrons in a solid is you start off solving for one electron, and then we'll make many later. Okay, so let's do the first model of free electron gas. So first model is the free electron gas. Okay, we know Schrodinger's equation. It's H psi equals E psi. So what am I going to make the Hamiltonian for a free electron gas?
Negative h bar squared over 2m del squared.
Psi. Anything else? Nothing else. Right? No potential energy. And how many particles am I talking about here? Just one.
So is this the total weight function, or is it slow for side?
What's that?
Are we doing time dependent or time independent?
No, I'm just doing the time independent.
And this is in the XYZ coordinates? Or is this
And three-dimensional, yeah. Right? And I'm not going to go through the full calculation, I just want to explain it. So in other words, what are these energies? What are these eigenenergies?
They're just like
They're just like EK eigenenergies. Okay, so what we did last time is we solved for the EKs. Right? We solved for those energy states, and they had to do with NX, NY, and NZ. And it was in like this Cartesian K-space. And then what we did is we converted that to a spherical K-space. And what we ultimately did is we converted to spherical K-space. Okay, now here's the key thing. When we converted to spherical K-space, what we did is we argued 2 electrons per state. Okay, what argument was that? So what gives it, why do we say only 2 electrons per state?
because of the spin up and spin down?
Because they're spin half fermions. And fermions obey the Pauli exclusion principle. So I never ever got all involved with the messy total antisymmetric wave function, did I? All right? I just threw in that argument right there. So it's very subtle, but I put it in there, right there. All right? But not in a hardcore way.
Because there has to be particles that put fermions can't.
Yeah, and I put it in there. I didn't include a total antisymmetric wave function, but it's there. It's part of that because we're making them, slamming them into only 2 into a state. All right? And then the other thing I said is, now let there be NQ electrons, where N is the number of atoms and Q is the number of valence electrons. So now what have I done? Now I made it many electron. And then when I did all this stuff, I came up finally with E Fermi equals equation
540.
543. If you could read it to me, it's h bar squared
Over 2n,
2m
3 rho pi squared to all to the 2/3.
to the 2/3. Okay, so I had a tough time coming up with words for this last time, so I worked on this. All right, so what does that represent, guys?
Energy below where all the electrons are filled or something.
Yeah, okay, but let's see if I can say it even better. Okay, it represents the level below which all the states are filled and above which they're empty. But is this energy, what
According
is
to
this?
the book, it's a separate boundaries occupied between the occupied and unoccupied states.
Right.
K space.
Yeah. All right, but let's look at it this way. Is this energy positive or negative?
It's
Hmm?
negative. But that equation.
Don't worry about the minus sign there. These
That
are,
equation is
that's kinetic energy, right?
good.
So this has to be,
Positive.
Positive.
It's all positive values, isn't it?
so that's positive, yeah. So in other words, here's the way I figured it out, right? And I'm not sure if it's 100% legit, right? But so far, it's 100% legit. Is the Fermi energy is the highest level of kinetic energy states that are filled. So check this out. How about if I say this? If I continue to do this as a one electron case, right, how many energies would I have gotten?
Is it continuous case?
If I had just done one electron,
Yeah.
how many wave functions would I have found?
We just want.
No, remember for an electron in a 1D well, how many did I find?
That's why.
No, wave functions did I find?
Oh, infinite.
Infinite number of wave functions and an infinite number of energies, right? Where the lowest one, and then I started having higher ones, right? So essentially, if I just left this as a one electron case, I would have just got a spectra of the kinetic energies possible. But what I did instead is I said, wait a minute, I have this spectra of kinetic energies, right? One electron state kinetic energies. But now what I'm going to do is take NQ total electrons and throw them into that spectra of kinetic energies. So, you know, out of this I might have got something like this.
So you,
I might have got chunk, 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 chunk. This is EK1, EK2, EK3.
the E Fermi is the one in which,
All right, and if I had just one electron, that one electron could be here, it could be there, it could be there, it could be there, it could be there, so on.
E Fermi put the top on the lower.
What E Fermi did is I said, okay,
Now
imagine I have this spectra of kinetic energy
it gives
states,
you a starting point somewhere in.
and now I have N electrons.
To give
Right.
it a
And I'm
starting
going to
point.
dump these N electrons into these kinetic energy states, but I'm only going to let 2 be in each one. How high does it go? Up, down, up, down, up, down, up, down, done. It fits right up to there. All right?
Basically, it's this E Fermi is your starting point for free electrons.
I don't want to say that. All I want to say is that your Fermi energy is the maximum kinetic energy that your electrons, it's first of all, the Fermi energy is a state of energy. All right? It's the highest state of kinetic energy for which you're guaranteed that the states of kinetic energy less than that are all filled, and the states of kinetic energy above that are empty. All right? And it's a positive number.
What, this doesn't include E potential yet, right?
Doesn't include potential. No potential, so these are positive energies. Now, if you want to think about it the following way, if we really did something like EK plus E potential times psi equals E times psi, what does this total energy come out to be? Positive or negative?
That's maybe.
That's negative, because all our cases are bound, so you get this like big negative energy. So this is like E total, and that's negative. If you want to think about it, the Fermi energy is just how high, how much you have filled up due to EK. Right? So the total energy you're bound, the electron's bound. But the kinetic energy is, you know, so the kinetic energy is the height above what you would have if you just had, if you had no kinetic energy, right? You would just have potential energy. Everybody would be sitting at the bottom of the well. All right? But if you have any kinetic energy, that's how high above the bottom of your well you would be. So for, if you include the total energy, indeed you are negative. But the Fermi energy is this level, which says that you're filled up until there.
Does E Fermi come in for scattering states when you're above this thing?
No. So scattering states are usually just 100% free. All right? So that's kind of what I wanted to say about the Fermi energy state, all right? Does that help at all? Does it make it more physical? And the way to make it more physical, guys, is get right down to the original problem. Boom. That's what we're solving. What is it? One electron. What does it have for the Hamiltonian? Kinetic energy. You can solve those energies and get the Fermi energy out of it. Okay? So then there were a bunch of homework problems on the Fermi energy. Problem 515 is find the average energy per free electron as a fraction of the Fermi energy.
That wasn't too bad.
And that's just pretty straightforward. It comes out to be 3/5 E Fermi.
I didn't find these that difficult.
These shouldn't, but these are plug and chug.
I did these well.
Yeah, good. All right, and that's what's amazing about it, I think. You know, it's just a very simple calculation.
Equations for each thing.
Okay, so then 516, the density of copper is 8.96 grams per centimeter cubed, and its atomic weight is 6.5 grams per mole. Calculate the Fermi energy for copper, assuming that copper has one valence electron. All right, and that number comes up to be about 7 eV. It's a positive number. That means that's about the kinetic energy that an electron in the metal would have. All right, now, it doesn't mean that it's free, all right, because the electron is still bound as a metal, right? It's still a metal. So ultimately, if you included the core, you know, you have all these free electrons going in the core, and you included the total potential energy that they were stuck in, it would be way down here. And what it's saying is that the copper is, you know, the highest level of electrons is, you know, 7.04 above however much it's bound by.
And you can go over that.
If you went over, it would be free. Yeah. All right. And so then that's how it's related to the next question is, at what temperature would the characteristic thermal temperature equal the Fermi temperature? All right, and what you do is you set kBT, which is kind of the total thermal energy. You set that equal to E Fermi and solve for T Fermi. And T Fermi comes out to be 8.17 times 10 to the 4th Kelvin. So what that means is that if you just had these electrons, right, and you had to assume that they had this energy because of temperature, what temperature would you have to raise it to so that the highest level kinetic energy electrons would be 7 eV? And the answer would be like 10 to the 4th Kelvin.
Almost 10 to the 5th.
Right. So if you're anything less than that temperature, right, then you're not thermally exciting those.
But they're not going to be solid at that temperature.
What's that?
At that temperature, it wouldn't be solid anyway.
Yeah, I mean, I
You're
don't
going to
know.
start getting into gas.
It will liquid. I don't know if it get gas, but 10 to the 4th, yeah, it
10 to
should.
the
That's
4th
pretty hot. That's
Celsius.
sun. Right? That's sun. All right.
Unless there's a lot of pressure.
All right. Yeah, but in other words, this stays pretty much electrons, you know, bound to this system somehow. You know, I'm not sure how, as a gas or liquid, all right? But the big point is that for copper, if you're less than 10 to the fourth, right, you can consider the copper being cold. And with the copper being cold, you know that the highest energy are about 7 eV above whatever it's bound. Okay? Okay, so then there are a couple other easy problems that are pretty straightforward. Okay, now we're going to go to the next level. And the next level is to improve. What are we doing? We've got solids with many atoms. All right, we did a free electron gas and then made that many atoms, but it had no potential. Now we're going to take the same model, all right, one electron. We're going to give it a kinetic energy, we're going to give it a potential, and then we're going to put in that it's fermions, so they obey the Pauli exclusion principle, and then there are a whole lot of them later on. All right, that's the model.
Once you solve it with the potential inlet, then you say, well, there's 2 per state, and then
That's right, and then make it n. So that's the idea, okay? So let's go to the next level. Okay, so the next level is, you know, the section 5.32, which is called band structure. All right, and we're going to be talking about block spin in particular. So let's take it to the next level. Let's add potential. For n atoms, right? But note, still 1 electron, all right? I'm still only going to solve for 1 electron, but what is my potential going to represent?
the 1 electron.
So my 1 electron, but what does the potential have to represent? It has to represent the n atoms, right? I haven't thrown in n electrons. I've only thrown in 1 electron, but my potential has n sites. Do you see that difference? Guys, what's that?
Each atom has 1, but the potential for each one.
It'll be a different.
No. So it's 1 electron. Look, here's a 1 electron in an infinite well.
Yeah.
That potential looks like this. Now it's 1 electron in a thing that looks like this. Yeah, how did he, yeah, that's how,
The direction spikes.
he calls it a Dirac cone. All right, so now it's 1 electron, but still. But what does the potential reflect? The potential that that 1 electron sits in has n bumps, not just 1. Where n goes to, you know, gets huge. Where these, they're 1, 2, 3, all the way to on the order of 10 to the 23rd. All right? Okay, so it's still 1 electron. So here's the scoop, is that we want, in particular, let's do quantum mechanics. So h psi equals E psi. So for this 1 electron, it's minus h bar squared over 2m del squared psi plus, okay, so now here's what I'm going to do. I'm going to write this v of x plus a psi equals E psi. So I'm going to space these bumps, these Dirac bumps, the Dirac cone or whatever you want to call it, the Dirac cone. I'm going to place those bumps about a apart, where a represents what?
The number of atoms.
No, not the number of atoms.
Bohr radius.
About the Bohr radius, or the Bohr diameter, whatever it is that will keep it apart.
The size of the board.
Yeah, where a is on the order of 10 to the minus 10 meters. Okay, so 1 electron atom. This is a 1 electron problem, but right now, what the potential looks like.
Is it really going to see all those atoms, or isn't it going to start to get screened?
Well, what happens is this wave function gets spread out, all right? And then what it's really going to say is the following. What this theorem is going to show is you essentially only have to solve it in one of these blocks, all right? And then it kind of repeats all the way around. But I still have to solve Schrodinger's equation, okay? And so right now, what this says simply is that I'm going to solve for a type. This is a type of potential that equals periodic.
Is that because you only have one electron?
What's that?
Is that because you have only one electron?
All I'm really saying right now is that the kinetic energy is 1 electron, and the potential is periodic, which says that the potential looks the same here, as it does here, as it does here, as it does there. That's all I've said right now. All right, now, I'm going to skip some here, because it just will take a while. But Bloch's theorem says the following. And what I want you to do for homework is to work through this in your books or in your notebooks. But I want you to bang your head against the wall on this stuff. All right? What Bloch's theorem says is the solution to this is psi of x equals e to the I n k a psi of x.
So it makes plus A.
No. All right? That the solution has to equal this. To get a solution to this, the solutions must look like this. And note, what that means is it means that e to the I n k a has to equal what?
The potential of A plus A.
For this to be true. 1. Okay, so this is Bloch's theorem. And to do it, here's the scoop. Here's how you do it. Bloch's theorem, outline it. All right? Bloch's theorem says something like this. Imagine that you had an operator that he called the displacement operator. And he called it d of f of x. And that equaled f of x plus a. So it displaced this. All right. Okay. What he then says, and it isn't proven here, it might be nice to look at, is this. He said H, where this is this Hamiltonian, H and D, guess what they do?
Commute.
They commute. So if you find the wave functions of the displacement operator, they should have the same wave function as the Hamiltonian. And this is exactly what you need here, because you want your wave function, if this is periodic, so it to be the same here, to be the same here, to be the same here, to be the same there. Because it shouldn't matter which one of those wells you're in. You don't even know which one it's in. All right, so there's subtle arguments, but that's how he goes about doing it. Right? I'm not going to do it in full detail, and he doesn't do it in a great deal of detail either. It's kind of a think about it type of argument. Okay? All right, but as a result of this discussion, Bloch's theorem, you get to this result. That the wave function has to have that form, from here. And this means that e to the I n k a has to equal 1, which means that k has to equal 2 pi n over the capital N A, where n equals 1, 2, 3 to infinity. So, once we've got that, then all we need, once we have that, all we need then is the solution for the psi of x inside one of these wells. Okay? And then once we get that, then we have our whole solution. So once we solve for psi of x, then we know that the psi of x, the solution to the periodic potential with n going to, 10 to the 23rd is equal to e to the I k n a psi of x, where this is the solution in one of the wells. Okay? Everybody kind of get it? So Bloch's theorem is super powerful. Everybody got it? So you could skip a lot of spaces in the future. When you have a periodic potential, you solve for it in one of those wells, and then you just multiply it by that phase.
Disregarding the solution with a sine kx.
Okay, so let's do this. If you go back to chapter 2, and I think what pages were there? Page 72 and 73.
Delta potential.
Pages 72 and 73. You do a problem inside the delta function. All right? And inside a delta function, and these might be negative potentials. I think these really should be going down. But if this is a delta function, what you do is you solve for the wave function in here, psi 2, and you solve for the wave function here, psi 1, and you solve for the wave function here in psi 3. Right? You solve for the wave function in each of the three regions. And then what do you do next?
You say, all right, where is 1 and 2 equal, where is 2 and 3
Right,
equal?
you've got to match things up, like it comes up like this. What you got to do is you've got to match the solutions at the boundary. And 72 and 73, you got to go back and look at this. It's really great to go back and look at it, and it really makes your head scratch. All right. But those two pages show how to match up the wave functions at the side of the potential. All right, it's really fantastic. All right, it's great. All right, but here's the kicker, guys. When you do this, okay, you end up with a condition, and the condition is equation 5.64, and it goes like this. Cosine of Ka, but this is capital K, and by the way, this is capital K, right here, this he calls capital K. So cosine of that same Ka equals cosine of little ka, and then plus m alpha. So there's a whole lot of constants that he put in over h bar squared k times sine ka. Right? And then what he does is he makes a couple substitutions. He makes a substitution that z equals ka, and that beta equals m alpha a over h bar squared. And what he ends up with is the following: is the cosine total kappa at Ka equals f of z, which equals f of z, which equals cosine z